Okay, now let's consider a solution made out of 60 milliliters of 0.50 molarity ammonia and 40 milliliters of 0.50 molarity ammonium ion. Let's say that your problem tells you it's ammonium chloride. We can go ahead and assume that this species is NH4+, and that the Cl- that goes along with it does not participate in the reaction because it is the conjugate base of a strong acid, and those don't participate. Okay, so the first step in attacking the question is figuring out if this solution mixture is going to behave like an acid or a base. So I open up my textbook and I check my Kb value for ammonia. It's weirdly familiar. It's actually the same number as it is for acetic acid, but it's a Kb, so it acts like a base. And then I'll go ahead and look up the Ka value of ammonium ion. 5.6 times 10 to the negative 10. Okay, so we see that we're going to be having a base situation here instead of an acidic situation. So when I write my reaction for this, I'm going to say, all right, I've got some water. My ammonia will react with that water to produce ammonium ions and hydroxide. Glorious. And then I feel like I should make an ice table and just like start plugging and chugging and going crazy with my numbers. But I take a deep breath and I realize that I can't just jump straight to plugging in molarities because I don't have the molarities of my resultant solution yet. First, I need to use an old friend of ours. M1V1 equals M2V2. To figure out the starting molarities of our ammonia and our ammonium ion. Okay, so let's take our ammonia first, and we'll do 0.5 molarity times our starting 60 milliliters equals our new starting concentration times 100 milliliters total. If you're curious where I got that, that's the 60 milliliters plus the 40 milliliters. Then I'll have a new starting concentration of ammonia that is 0.30 molarity. Okay, now the ammonium ion. That one also starts at 0.5 molarity, but there's 40 milliliters of it instead. Okay, so when you do the math for that guy, the starting concentration of NH4+ is 0.2 molarity. Okay, now we're good to start an ice table. Okay, so let's start filling in our table. We started with 0.30 molarity for the ammonia and 0.20 molarity for the ammonium ion, and then we're going to assume we start with no hydroxide. According to Le Chatelier's principle, we'll shift to the right to fill that zero. And then we'll end up with 0.30 minus x, 0.20 plus x, and x. Now, our minus x and our plus x here are going to be so small that they're insignificant. And we can tell because our starting concentrations are like 1,000 times bigger than our K value, maybe even 10,000 times bigger. It's a lot bigger. So that change is going to be really, really small. So I'm going to go ahead and estimate that those small changes are 0. And then set up my K equation. My Kb for this case is going to be the ammonium ion times the hydroxide ion divided by the ammonia molecule. Glorious. So we'll have 1.8 times 10 to the negative 5 equal to 0.20 times x over 0.30. I'll multiply that 0.3 over and divide by the 0.2 to get an x value of 2.7 times 10 to the negative 5. Now remember to be really careful here. Some of my students go ahead and shove that number into a negative log. That is not your hydrogen ion concentration. So if you did negative log right now, you would end up getting a POH. So just be careful. We can use our KW expression to convert our hydroxide concentration into a hydrogen concentration. Okay, so we'll have our 10 to the negative 14 equals hydrogen ion concentration times this ugly number. And we'll end up getting our hydrogen concentration is equal to 3.7 times 10 to the negative 10. When you take the negative log of the hydrogen ion concentration, we get a logical answer. Considering our situation is basic, we'll get 9.43 as our answer. And again, this makes sense because our solution is acting like a base.